This is the screencast for section 6.3, example 2, repeated use of integration by parts. All right, so in example 1, you learned how to use integration by parts, and one of the tricks I told you was make your u something that when you take its derivative is going to make your life easier. It's going to maybe reduce the exponent a little bit. Well, in this situation, your exponent here is squared. So that's kind of a clue that we might have to do integration by parts more than once so we can eventually make that easy integration of v times du. Alright, so first of all, we have a product of two functions. They are not related by a derivative, so I'm guessing I'm going to have to use integration by parts. I need to identify u as something I take the derivative of, and then dv as the other function I take the antiderivative of. So I'm going to call u x squared, and I'm going to call dv then e to the x. If I took the derivative of e to the x, nothing would change. The derivative of e to the x is still e to the x, e to the x, e to the x. So nothing would change. So I'm going to make dv e to the x. So I'm going to take the derivative then of u, which I get 2x dx, and then I take the antiderivative of dv, and I get v e to the x. So now I can plug that into my formula. U times v minus the antiderivative of v times du. So in example 1, here's where you would have been able to just take the antiderivative, throw a plus c down, and be done. But unfortunately, the antiderivative of e to the x 2x is still a product of two functions that I don't know the antiderivative of as a product. So I'm going to have to use integration by parts again. Now, when you use repeated use of integration by parts, you want to keep u in line with what u was before, and dv in line with what dv was before. So in this case, u isn't going to be x squared necessarily, but u is going to be 2x, the portion that came from x squared. And then dv is going to be e to the x, the same as it was before. Alright, so take the derivative of u, and now I have just 2 dx, and then take the antiderivative of dv, which is e to the x. But first, remember, you have x squared e to the x minus that really stayed the same from the previous problem. We're only subtracting an integration by parts to figure out this antiderivative. So x squared e to the x stays out in front, and then we're going to subtract now the integration by parts used for this product in an antiderivative. So now we're going to use our integration by parts formula. There's u times v minus the antiderivative then of v times du. Now this is an antiderivative that I can take. The antiderivative of 2e to the x, well, the coefficient 2 just stays outside of the integral sign, and so I'm really taking the antiderivative of e to the x, which is e to the x. So now this inside would be 2x e to the x minus my 2e to the x, the antiderivative, and of course, don't forget your plus c. Now distribute that negative sign, and I have x squared e to the x from the very first integration by parts minus 2x e to the x, and then now plus 2e to the x plus c. Now try problem number 5. Also find the indefinite integral. So we do not have a lower limit of integration and upper limit of integration. It's just indefinite. I see a product of two functions, x squared and cosine of x. Now cosine of x has a pattern of differentiation. The derivative of cosine of x is negative sine of x. The derivative of negative sine of x would be negative cosine of x. And we just have this infinite repetition if I take the derivative. So taking the derivative of cosine of x isn't really going to benefit me. Taking the derivative of x squared, though, will benefit me. So I'm going to call u x squared, and then dv is cosine of x. So I'm going to take the derivative of u to get du equals 2x dx, and I'm going to take the antiderivative of dv, which is sine of x. Now I've got all the parts I need for my formula. There's u times v, or sine of x, minus the antiderivative of v again, times du. Now again, I'm in a situation where I can't just take this antiderivative. I've got the sine of x and 2x, which are both functions of x being multiplied together. I've got a product here. It's not just like I have a coefficient of 2 that I can put outside the antiderivative. So I'm going to have to use integration by parts again. So again, I'm going to stick with u being 2x, and then dv is now going to be sine of x, so related to the u and dv from before. The derivative of u is 2 dx, and then the antiderivative of dv is negative cosine of x. So I have x squared sine of x minus the integration by parts that I'm going to do for this antiderivative piece here. So this came from the first integration by parts. Now I'm going to break down a second integration by parts. So my new u times my new v minus the antiderivative of v again times du. So now I've got negative 2 that can be taken outside the antiderivative, and really I'm just taking the antiderivative of cosine, which I know is sine. So I have the two negatives cancel out and make a positive 2 sine of x. Now I'm going to distribute the minus sign that came from the original antiderivative or antidifferentiation by parts. And of course I've got my plus c at the end there. And there's my final answer, x squared sine of x plus 2x cosine of x minus 2 sine of x plus c.